introducing Dr. Gerald Pollack from the University of Washington, where he's a professor of bioengineering, and for the past 10 years he has been looking at electrical structures in water. His presentation last year was extremely compelling, and I'm hoping that he'll review some of that territory as he also brings us some of his new work and brings us up to speed on what he's doing and the implications of his work for the future. So please welcome to the stage Dr. Pollack.
Well, thanks, David. Actually, I got a prop here. They gave me some water, but the topic of the day is not water. I love to talk about water. It's so interesting. It's so full of charges, and it fits so well with the electric universe. But I want to talk about something else today. I want to talk about the Institute for Venture Science. A few of you may remember, I don't know how many of you are new or not new, we talked about this last year at the meeting, and this is really a kind of progress report, though I will start with some rationale for those of you who were not here, because the first thing you may be wondering is what's the Institute for Venture Science, and what's venture science, and why bother with all this? So what I want to do today, the agenda is as follows. First of all, is it really true, as Martin Lopez Corredora says in his recent book, that this is the twilight of the scientific age? I'm not sure how you feel about that, but okay. And then the issue of, is there really a chronic decline in science as we see it compared to, say, 100 years ago with the Einsteins and the Plancks and people like that? Is the chronic decline curable? And how can the Institute for Venture Science bring a cure to this syndrome? And I want to tell you the current status of the Institute for Venture Science. Okay, so we start with an idea that you may have. And the idea is, let's say, a round Earth idea. So you come up with this brilliant idea that the Earth is round, and everybody around you knows for sure that the Earth is flat. You think, well, you know, this is a pretty cool idea, and it's awfully important that the Earth is round. And the question is, if you do this today, if you were to come up with this idea, what chance would you have with this revolutionary idea to gain some traction, gain some success? You might think an idea as compelling as this would attract a lot of interest and perhaps trigger some kind of revolution. But you know, if recent experience is a guide, it doesn't happen that way, because we haven't seen a whole lot of revolutions in the past 30 or 40 or 50 years. So think about the number of revolutions that we've had since, let's say, 1970 or so. That's a pretty arbitrary date. Now, what I'm asking you to think about is, in terms of revolutions, we're talking about a conceptual revolution. We're not talking about technological revolutions which are supported by industry. And there have been quite a few of those. I mean, everything related to the internet and such. But that's not what I'm talking about. I'm talking about a conceptual revolution, some new idea that has never really been considered before, that changes our outlook of the world. And I'm looking at realized revolutions. If you read the New York Times or even Wall Street Journal, it tells you about this new promising drug that has the capacity to cure cancer. It has the capacity, it's promised, but it's not realized. They hardly ever come to the realization. So what I'm talking about is something like, for example, the splitting of the atom. That's a conceptual revolution. That was 70 years ago. Another one is the structure of DNA. That was 1953. So that was, I think, 61 years ago. And it led to all kinds of interesting things about the human genome and such. And so that's what I mean by conceptual revolutions, a new concept that changed our ability and led to so many new technologies in the future. So I ask you, to think for a moment, how many modern conceptual realized revolutions can you think of? I give you 30 seconds. You're having a difficult time? Yes. Okay. Now I know that some of you can actually think of one or two. I ask this question to many people, and I get a blank look. That's the response. I think there's been one, and I'll mention it later. I think only one that I know of, and it's in the medical sciences. We'll come to that a bit later. But, you know, the editors of Science, in their 125th anniversary edition in 2005, decided to do exactly that. They tracked the revolutions that have occurred in science from the time of the Greeks to 2005. And this was done in a kind of fold-out page that, well, it was kind of like a Playboy fold-out page, except the pictures were less interesting. You know, there's a picture of Einstein and what he did, and Max Planck and so on. So I conducted an exercise. I made two lists. I took the names of people and what they contributed from 2005 back 40 years. And I did the same thing a century ago, from 1905 back 40 years. And this is a sampling of the old list. Now, I bet you that everybody in the audience knows every single one or almost every one. I took the full list, in fact, and I gave it to many people, scientists and non-scientists, and almost everybody was able to identify almost everybody on the list, no question. And then I took the modern list. And here's, again, this is a random sampling from about 15 different people. How many of you can identify 0 of these people? Okay. Something is the matter here. How come? Now we're talking about from 1965, right? So we're talking extending back a half century, you know, so you might say, well, some of this stuff, you know, it just takes a lot of time for revolutions to occur, you know, but since we know that political revolutions can take place overnight practically, how come it takes 50 years for this to happen? Something something is different. It really is true that there are very few revolutions that have occurred. These people actually have done important things. Carrie Mullis, for example, was involved in developing the PCR method of amplifying DNA. It was not exactly a conceptual revolution, it was a technological revolution. And another of these scientists figured out how to culture stem cells, which made possible a lot of interesting experiments, but they're not really the kinds of discoveries that are comparable to Einstein or Planck or Curie or what have you. Okay, so why challenge conventional thinking with revolutionary ideas? Aren't we making great progress? We're making huge progress. The number of papers that are published exceed the number of papers ever published in history. It's amazing how many, but the question is, you know, what new understanding do we have from all of that knowledge? Of course, we advance through revolutions. This is just a few examples. But the problem now is that revolutions are really sparse. There's something wrong. Something is going on. We had lots of revolutions 100 years ago, but it's really hard to identify revolution in the past year. So why so few revolutions? Well, as you know, revolutionary ideas challenge the status quo. And these threaten the stakeholders in the prevailing paradigm and threaten the grant reviewers. And you know what happens when people get threatened. They respond. And so most scientists understand that if you threaten the stakeholders, you have to be careful. And particularly in the institutions that I deal with all the time, the National Institutes of Health and the National Science Foundation, most scientists with revolutionary ideas keep it secret. They don't apply. Once they apply, they know they won't get the money, and also they develop a reputation as being the kind of person who you stay away from. So revolutionary a change is suppressed as a result, I think, largely of the institutions that we have that fund science. So modern science the tree of knowledge may look something like this, but the modern dwelling place of most science is up here at the periphery of the tree of knowledge. This place is safe. You don't shake the tree. You don't pull off a big limb. And it's non-disruptive. So everybody's happy. You know, a lot of papers are being published, the news releases, press releases from every institution show great progress and real promise for the future, but not many revolutions. So the revolutionary progress comes when when someone discovers that, you know, one of these limbs is not really as sound as we expect, and you prune the limb and come up with some brand new growth. And so one example of that is very familiar here is the heliocentric solar system. Once that happened, then everything changed. This was a new limb on the tree of knowledge. Another one in the medical realm is the one by Semmelweis, who found out that if you wash your hands before you deliver babies or conduct surgery, the patient is more likely to survive. Of course, he was brushed aside, and he died insane from all the pressure that was put upon him. So the new growth is really what we're looking for, and which gives you a revolutionary advance. It's kind of like, you know, you look at something, and this looks great. It's obviously this is a rectangle, but you know, you look at it from another direction, and it's a different reality, a fresh perspective that teaches you something different. So today, this is the issue. We have a huge amount of money that is put into science. If you add up, just in the US, the National Institutes of Health and the National Science Foundation, it's approximately $40 billion. If you add defense and such, it's probably up to $100 billion just in the US. It's a lot of money, but very few revolutions. And if you compare that to 100 years ago, almost no money. There was some. It's a kind of paradox, isn't it? I'm glad there's some humor in this. But something is wrong here, because we got a lot of input, but no output. A lot of promise, but no real revolutions. So why is this the case? Well, I kind of alluded to it. You can think of a few ideas. Maybe scientists are stupider than they were 100 years ago. It could be, you know, the environment is having some real negative impact on us. Maybe we're eating the wrong food, or the electromagnetic pollution or something. So that, I guess that's one idea. We hope that the increase of stupidity is somehow compensated by the larger numbers doing it. Maybe the problems are harder. I don't know, but I've seen no evidence that the problems are harder now than they were 100 years ago. Or another possibility is, well, everything is already known. Therefore, you know, there's nothing no revolutions to occur. And I know what you folks think about that. So I think what I alluded to before is it's the culture of science today that is the culprit. The emphasis on productivity, producing lots of papers, competing to get into the prestigious journals and such. And so it's a culture where power is really important, that power is given to the experts and power is given to the vested interests. We need money to do research. The experts are the ones who decide whether the revolutionaries get the money or don't get the money. This is not a system to encourage radical thinking and fresh ideas. So you come up with a fresh idea, and the typical response from the establishment is something like this, you know, you're proposing what? Yuck. So this is the kind of, you know, I think many of you have been there. This is the kind of response. What I've discovered is that there actually are plenty of round earth ideas out there. I study water, but I've been in several different fields during my career. And I used to think the first field that I entered, which was actually cardiac cell electrophysiology. I kind of started in biology, and I thought there were prevailing views, but there were challenging views out there, and nobody took them seriously. And I thought, this is a problem. And then I entered into cell biology, and I saw the same problem. And then I entered into muscle contraction, and I saw the same problem, a theory that has been around since 1954, believed by everybody, but the evidence is so clearly against it, and the people who have evidence against have no ability to make any inroads against the establishment. So I came to realize that this is true in numerous fields. I think the people around here, some of you may believe it's true in the electric universe area, but this is endemic. It's just all over science. Usually what happens is the response that I've seen among many people is the response to a round earth idea in a flat earth environment. Well, if the idea is any good, it would have been discovered earlier, and everybody would know it's true, and blah, blah, blah. And so your idea can't be any good, because obviously that hasn't happened. The case closed. Just to give you a couple of ideas of some of the, what I think are kind of interesting ideas out there. Of course, the energy idea, tapping energy from the environment, starts way back from Tesla. But there was a particular invention that I came across, which kind of interesting because it capitalizes on the Earth's electric field. And it looks something like this. It looks complicated, but the principle is really simple. These are balloons way up, and they're actually there to suspend a metallic ring. And since the electrical potential in the atmosphere is something like 100 volts per meter, you have a potential difference between this metallic ring and ground. And if you put a motor in between, the potential difference between here and here is enough to drive that motor. And there were a lot of electrostatic motors that ran on low current, high voltage many years ago, and are still being developed and can produce on the order of 75 to 100 watts of mechanical energy, which is, pretty substantial. And these have not really seen the light of day. And here's another example. This is a lifter. And some of you know about lifters. It just, you have one electrode here, this aluminum foil, and the other electrode is a wire up at the top, which you can barely see. You put a potential difference of 10,000 volts between them, and this lifts up. We have one in my laboratory. It lifts up easily to a meter. It's just putting a potential difference of 10,000 volts, that's all, and you get lifting as a result of that. My estimate is that nobody knows how it works. Of course, we have some ideas, but this is the kind of thing that would seem to demand some development and some understanding. But I bet many of you have never heard of these lifters. And in the area of health also, my favorite is always this one. It's a book that's called The Doctor Who Cures Cancer. And this is Emilio Revici, who died about 10 years ago at the age of 100. And he had the reputation of if someone was really sick and cancer and they were just about gone, they go to Revici. And Revici was able to do it. This is a quote from the guy who was the retiring president of the Sloan Kettering Cancer Research Center, which is perhaps the most distinguished one in the US, in New York. And he said, the quote on the back, "I don't know how he does it, but people walk in dead and walk out alive." I come into contact with a lot of people who deal with alternative health. And I'm amazed by the progress that these people have made and the ability of these people to actually cure people with cancer who can't be cured by the standard chemotherapy, radiation surgery that's been used effectively for 50 years, just minor technological improvements. So another area that needs to be dealt with new, fresh, information and fresh ideas. So problems remain unsolved. The two I mentioned, plus understanding how our brains work and Alzheimer's disease, function, dysfunction, combating global warming if you believe in it, or establishing that it's not true, which some colleagues, I just spoke at NASA, there's a big group of people who are absolutely certain that there's no warming. This needs to be straightened out. Eliminating starvation and many others. Okay, so I've given you the background, I've given you the problems, and I've given you maybe some evidence about that new book I mentioned, that the decline of the twilight of the scientific age. We're not producing what we used to produce in science. So we decided to see if we can do something about it, and we decided to put together a foundation that funds promising ideas that challenge conventional thinking. Now, obviously, we have no building, or this is just a sort of dream for the future. We call it the Institute for Venture Science, or IVS. And this institute is a funding agency. It funds promising ideas that challenge conventional views. And there are a few twists to it that I want to tell you about it that I think will make it operate effectively. So how will we foster the kind of revolutionary advance that we know is missing now? We need it. We need it badly to solve our problems. So the first is that we invite groundbreaking proposals. It doesn't matter what field. Anybody who has an earth-shaking idea, a round earth idea in a flat earth environment, send it to us. And we, of course, put it through a vetting process. I won't go into detail about the initial entry. We don't want flaky proposals, obviously. We want substantial ones. We ask the flat earth people to please tell us what's wrong with this round earth proposal. And you can guess how scathing their review is going to be. We know that. Okay, so you have the round earth applicant, and you have a bunch of flat earth people feeding back and saying, this is the biggest bullshit I ever, but give us some reasons why you think it's not right. And so we establish a debate between the two. And the people who listen to this debate are outside the field. They don't care whether the earth is round. They may care, but they have no bias as to whether the earth is round or whether the earth is flat. They want to listen. They want to hear how well this applicant can defend himself against those tigers and lions. And then what happens is we make judgment as to how well they did and how important their subject is. It's the product of those two that determines their score. We fund the selected proposals liberally because, people who venture into the real unknown, often they need substantial funds, and they need to have the confidence that they're going to be funded for some years at least. Otherwise, it's too risky to go into. There are human issues that need to be taken into account. Now, here's the key. I haven't told you the real key. The real key is next. The real key is that we fund multiple groups pursuing the same theme. So we get the round earth idea, we fund the round earth idea, and we try to identify around the world 10 or 12 different groups who also think that the earth might be round, but they're using different techniques to check it. And so what that does is it creates a critical mass. It's easy to dismiss one person as a crackpot. Stay away from that person because their ideas are really weird and you'll never get anywhere. But when a dozen groups come to the annual meeting of the Shape of the Earth Society and, hey, what's going on here? There are a dozen groups reporting that the Earth is round instead of flat, then they have to pay attention. So the single one is dismissed, but the multiplicity is really the critical factor that can make a difference and that can bring revolutions. If the round earth really has the goods, within 2 or 3 or 4 years, it'll be obvious that that the evidence for this is convincing. And I think within a few years there'll be a phase transition, a new way of thinking, a revolution. On the other hand, if the round earth people don't really have the evidence and the earth is flat, they'll have to defend themselves. And then we'll know for sure that the earth is flat, but we'll be more certain of it. So either way, the investment is good investment because both sides are put on the same platform to debate, and then we learn which one is correct. And I think many of these will lead to revolutions. Okay, so how do we do this? Well, we have a funding goal. And the funding goal it's sort of arbitrary, but we're thinking of an endowment, say, on the order of $10 billion. And from that endowment, we could use the interest, which at 5% is something like, well, $500 million. Now, for $500 million, if you think of that each project, let's say, arbitrarily gets $1 million per year, just arbitrarily, some need less, others may need more, that's enough to fund 50 revolutionary ideas times, say, 10 labs per idea simultaneously. Now, it sounds like a lot of bucks, but it's less than 1% of the US annual research budget. This annual budget, less than 1%, and for that, we anticipate out of this will come multiple revolutions. And the present course has produced almost no revolutions at much higher annual budget. So if you think about what happens, you get revolutions, and from revolutions you get fresh insight about the workings of the world, new solutions to all the problems that plague the world, and a bright future. And for those who are, more practically minded, think about what revolutions can do. Every revolution, every new concept leads to many new technologies, inevitably, and economic revitalization, and again, a bright future. So if you think about the prospects, what this can bring, and think about, well, how do you get people to donate? We're looking for private donors. It's very easy to donate to something like the Gates Foundation, which, by the way, is right around the corner from us. This guy was actually the boss of my son when he was young. So Bill Gates formed the Gates Foundation. And, if you put in money to the Gates Foundation or other foundations, they do good. And you all know that the Gates Foundation has been making real progress, producing vaccines that some of us think are good and others think are not so good, and producing sanitary conditions and toilets and such. So people are tempted to donate. Now, what's different about us is we promise something beyond that. It's a kind of amplification effect. You put in a small amount of money and you can get potentially huge dividends out of it. I just give you one example. So, a few scientists were playing around with impurities in semiconductor materials about 60, 70 years ago. And out of that came transistors and diodes and photodiodes, and now digital cameras and solar cells and integrated circuits, microprocessors, laptops, smartphones. Basically, everything we do today came from a discovery of physicists and engineers working at the fundamental level. And that's what we're talking about, funding some capsule of an idea. And who knows what that can lead to. It's unpredictable, but it can be awfully big. Now, there are quite a few billionaires out there. Some of you know that many of them signed the giving pledge that was suggested by Bill Gates, which means that ultimately many people will be donating a large or substantial amount to various charities. Many want to give back to society, and many want to leave a legacy. They want to be remembered. Bill Gates, I would guess, wants to be remembered not for being the richest guy in the world, but for having founded the Gates Foundation, which did many good things. So that's an idea. And of course, if someone is willing to donate a couple of $billion, it's possible that this could be part of the legacy. Now, why can we make this happen? Well, I think we have a we assembled a very interesting and capable group of people. So let me tell you about our advisory panel, the people who we ask for advice and they come back and give us advice. And I'll just read to you to give you some idea of the distinction of these people. Michael Crosby was the executive director of the National Science Board, which runs the NSF. He also was a vice chancellor of a university. Peter Katona was the president of the Whitaker Foundation, which funded bioengineering. John Strauss was the CFO of the Howard Hughes Medical Institute, and he's been president of 4 universities. I guess they didn't like him so much. Alexander Konovalov was the rector of Kazan University in Russia. That's the 3rd-ranked university in all of Russia, and was also the head of a large chemical institute. And for those of you interested in homeopathy, he has brilliant results now that can explain how this really works. Barry Marshall, you may not recognize his name, Nobel laureate from Western Australia. He's a guy who I think was responsible for one of the few revolutions, that is, finding out that ulcers were not necessarily caused by worrying, but by bacteria. He had a difficult time of it, and maybe you know that eventually he swallowed the bacteria, he got an ulcer, and he cured himself with an antibiotic, and then they gave him a Nobel Prize. Stane Pechovnik was the rector, just retired, of Ljubljana University, and a member of the National Science Board, Doug Randall. And Don Miller is a guy who I know in Seattle, and he was chief of cardiovascular surgery and also a well-known philosopher of science. Very deep understanding of the scientific processes. So that's the advisory panel. And the core group, the executive staff, I think is a group we're committed with complementary skills. And you may know some because there are some people who are floating around here. And James Ryder, who used to be the vice president of Lockheed Martin, Frank Costanzo, who's around here today, and who's been a senior level political advisor and has turned around many businesses. Susan Chirac, you know, was an HMO executive, and myself. And so I think with the devotion of this executive staff and the advisory panel, I think we have a chance to make it happen. The website is under construction, and we hope that it will be up, and you can look at it within the next few weeks. That's really our starting point, something that we need in order to launch, realistically, the campaign to get funded. So the Institute for Venture Science, we're talking about unthinkable ideas today and received wisdom tomorrow. Thank you. Thank you. Thank you.